So welcome everyone to the first CTNS event of the 21-22 academic year. I'm Bob Russell, the Ian G. Barber Professor of Theology and Science at the GTU, and I am also the founder and director of the Center for Theology and Natural Sciences, which is presenting this event tonight. This is a momentous year for CTNS. It is our 40th anniversary, if you can believe it. I began CTNS in the fall of 1981 as its founding director and assistant professor of theology and science. For 35 years, CTNS was a separately incorporated organization affiliated with the Graduate Theological Union. In 2016, we became an internal program of the GTU, giving us a lasting institutional and programmatic foundation. The mission of CTNS is to promote the creative mutual interaction between theology and science in three program areas: research, teaching, and public service. And tonight's Russell Family Fellowship program is part of all three of those. So it really is the apex of our year. Tonight's fellow, I will introduce in a second. And Dr. Wegter-McNelly's lecture tonight will be called A Strigilated Universe. Our agenda will start with Kirk's forum presentation, followed by a very short response by Hung Jo, and then a time for Q&A. We'll close about 6:45. So I'm very proud to introduce Kirk Wegter-McNelly, the Donna and Marshall Robinson Assistant Professor of Science, Philosophy, and Religion at Union College, which is in Schenectady, New York. Kirk is a beloved GTU graduate, studying with Ted Peters and me. His work focuses primarily on the implications of contemporary physics for our understanding of humanity, the cosmos, and God. He is the author of, I think, one of the best books in the field, The Entangled God, Divine Relationality and Quantum Physics. That's Routledge 2011. And he co-authored 2 volumes, one of the 5 volumes in our Vatican Observatory CTNS series called Quantum Mechanics, Scientific Perspectives of Divine Action, that was 2002. And from our Science and Spiritual Quest program, he published SSQ, New Essays by Leading Scientists, back in 2002, again, Routledge. It's a pleasure having Kirk as our 40th Russell Family Fellowship. I think it's really appropriate that Kirk is someone who came to the GTU with a background in physics and theology, and did his PhD in this challenging world and went on to have a terrific career in the academic world and great publications. And now it's a pleasure to welcome you home, Kirk, to give our Russell Family Fellowship. I'll just say before you start, tonight's respondent is Dr. Hung Jo Lee, who holds a PhD in theoretical physics, and Hung Jo is currently a doctoral student studying with me for his second PhD, this time in theology and science. And he'll be a respondent at the end of at Saturday's conference as well as tonight. Okay, let us begin. Kirk, thank you for accepting the 2021 Russell Family Fellowship and for leading us tonight in this fascinating conversation about a strigilated universe. Take it away, Kirk.
All right. Well, thank you, Bob. It's a real pleasure, an honor, and a privilege to be this year's Family Fellow. And I'm pleased to talk with you all tonight. Thank you for coming out or staying in, whichever it is. Tonight, yes, I am going to be talking about what it means to talk about our universe as a strigilated universe, the cosmogonic significance of primordial gravitational radiation. So I'm going to share my screen. I'm hoping that you all can see that. Yeah, good. Okay, so what I'd like to do tonight is just a brief overview first. I'd like to talk a little bit about the question of cosmic origins from a religious and a scientific perspective to just sort of set the scene. Then I'd like to talk specifically about cosmogony as one aspect of cosmology having to do with the question of origins. And in particular tonight, the question of temporal origin. Then I'd like to talk a little bit about the Big Bang model and some of the alternatives that have been proposed, why those alternatives have been proposed, and sort of where things stand with the status of the Big Bang model as sort of the standard view of how our universe came to be and came to evolve. Then I'd like to introduce you, if you're not familiar, to a relatively new branch of physics called gravitational wave physics. It has its origins in the work of Einstein in the early 20th century. It's a result of, a consequence of his theory of gravity, his general theory of relativity. And there was a lot of debate and confusion for a number of decades after he first introduced his theory of gravity about whether these were real, whether they were an artifact of the theory. It's very difficult in terms of the math and understanding what the physical implications were. Einstein vacillated himself, thinking in some moments that they were real and in other moments that they weren't. It turns out that they are. It took about a century for the physics community to catch up, and particularly the experimentalists. And in 2015, the first detection of gravitational waves happened. So I'd like to introduce you to that generally, and then talk specifically about one kind of gravitational wave. There are lots of different sources out in the universe of gravitational waves, but the one that I'm particularly interested in is the universe itself in its very earliest moments as a source of gravitational waves. Those are known in the literature as primordial gravitational waves or primordial gravitational radiation. Then I would like to round out my comments by talking a little bit about cosmic beginnings in light of gravitational wave physics, and thinking a little bit, like to think a little bit out loud with you about where science fits in the theological picture when it comes to thinking about cosmic origins. So, first, where do we come from? Cosmology is, of course, the general term, although it's appropriated by science today. More generally, it means the study of and interest in our universe, in the cosmos. Cosmos comes from, cosmology comes from the word cosmeo, which means order or beauty. So we don't live in just an agglomeration of objects and space. We live in a place that seems to exhibit some kind of order. And that order is interesting, and it turns out not only worth studying, but it's possible to study the order. We live in an age Max Tegmark calls our own age the age of precision cosmology. He says they used to practice derision cosmology. Nobody really took them seriously, but the experiments and the instrumentation have come a very long ways, and it's really quite remarkable how much we do know about the cosmos. Within cosmology, as I mentioned, is the idea of cosmogony, where things come from. And that's what I'm most interested in. I think science can shed some interesting light on questions that, traditionally speaking, were regarded as either theological or philosophical. And I'm going to try to make that case to you tonight. First, I want to say just briefly about religious cosmogony. It can seem very speculative, and there's always been a temptation to a kind of literal interpretation of cosmogonic myths in religion. I don't think that's really what's primarily going on in the world's religions that have cosmogonic myth stories. The upper image that you're looking at is an Egyptian image that's Shu, the god of air, separating daughter Nut, the goddess of the sky, and son Geb, god of the earth. Right, so you've got this image of one god holding up a goddess who is the god of the sky, and then the god of the earth beneath. Right, a cosmological image, but also a kind of cosmogonical story about how the world came to be and why we have the upper and the lower reaches of our world. The lower image gives you a sense of one of the practical, I think, implications and benefits of having a cosmogony, particularly if you happen to be Pharaoh in this case. This is a pillow, essentially. It's a headrest that the pharaohs would have used to sleep. And this is the god Shu, in fact, holding up the pharaoh's head, just as in the upper image, Shu is holding up the goddess Nut of the sky. So if there's any sort of practical significance to this, it's that it warrants, the very structure of society. The fact that the king, that the pharaoh puts his head to rest on, and a god holds it up as he sleeps, suggests that there's a kind of authorization going on here, that the myth authorizes a certain kind of a claim to power and leadership. So speculative, in fact, I think quite practical in terms of the kinds of the ways in which the stories get used in cultures. Scientific cosmogony, on the other hand, is quite a different thing. It's investigative. It's interested in natural processes, in laws, and including where those laws come from. It's not entirely clear even today whether that's a scientific question or not, the origin of the laws themselves. I think there are a lot of scientific cosmologists who certainly hope that the laws will explain themselves as self-evident once we have them, that it will be clear why they are what they are and why they couldn't be anything else. That may not be the case, though. There's no reason why it has to be. And the origin of the laws that describe or govern our universe may just be beyond our reach, but we'll never know if we don't investigate. So a little bit more about religious cosmogony. There are a variety of cosmogonies that one finds in the religions of the world across the globe. I've listed a number of them here. There is the idea of generation from a primal substance, from perhaps a seed or an egg. Some cosmogonic myths create the world as a result of sexual union of a primal male and female reality. Ordering of chaos is another way that cosmogonic myths are told, or of some sort of pre-existent matter. Christianity, some of you will know, has come up with this idea of creation out of nothing. This is a long-standing doctrine within the Christian tradition, that God doesn't use pre-existing matter or doesn't have to tame the chaos. God just creates out of absolutely nothing, a strong affirmation of divine power. Finally, there are traditions that refuse to speculate. The Buddha famously said, when the house is burning down, you don't ask how the fire started. That's not your chief interest in the moment. The interest is getting out of the house. And if the world is full of suffering, then where does the world come from? Where does suffering come from? Well, that's not the question we need to be asking right now. He said, we need to be helping people out of their suffering. So there are some religious traditions that just set it aside as a kind of speculative question that's not all that important. It is certainly important in the Western traditions. And as I suggested earlier, it's not just a speculative kind of enterprise, cosmogonic myth making. It roots the renewal of the natural world. It is a story that gives sense and meaning to human life and a sense of of how we sustain ourselves and how God or the gods sustain us. And in the case of the pharaoh, I think it's about maintaining social institutions, maintaining authority and power. So cosmogonic myths do a lot of practical work in cultures, even though they can seem quite speculative and at times strange. Cosmogonic myths are not only about temporal beginnings, but that is another thing that they're about. Cosmogonic myths they're ideological. They explain where the world comes from. And many of them have a kind of temporal beginning included in the story. And that's particularly what I want to focus on tonight. I wanted to give you just a brief background to a sort of the larger view of cosmogony and cosmology, so as not to suggest that this is the only interesting thing about cosmology and cosmogony, but it is an interesting thing about it. And I think it's something that science has begun to talk about a bit and begun to offer some insight into. So Western religious cosmogony in particular has been quite interested in the question of whether there is a beginning or not. The biblical message in the Hebrew Bible is a kind of creation out of chaos, out of the Tehom. Plato talked about the world being created by a demiurge or a craftsman, a kind of subordinate god, or possibly the divine principle of creative power. Not clear how literally or figuratively Plato thought about the demiurge. Aristotle, a kind of different, quite strikingly different view. Aristotle argued that the world, in fact, has no beginning, and that the world is eternally old. I mentioned the Christian notion of creation out of nothing, or creatio ex nihilo. It's not, strictly speaking, a biblical view. The Bible talks about creation out of the depths, the abyss, the chaos. But Christian theologians took this idea, took the biblical witness and reshaped it in their own context, because they were looking for, I think, a way of affirming divine sovereignty against dualistic traditions at the time that wanted to argue that either that creation happened as a result of, a cosmic battle, divine conflict, or some other kind of give and take between God and pre-existing matter, say. So the affirmation of creation out of nothing really asserts against all of those other views that creation only involves God and nothing else. Augustine put his own sort of interesting twist on this tradition. He gave us the idea that creation is not something that happens in time, but rather time is part of creation. Creation includes time. There was no time before creation. There is only the time of creation. God's creative act, for Augustine, is eternal. This has been a sort of dominant view, widely adopted in Western theology, and it carried on into the Middle Ages and into the Reformers and even into the present. One to register Aquinas in the late Middle Ages, who did acknowledge that the church and Augustine had this view of a kind of temporal beginning to the world. He, of course, famously synthesized much of his own Christian tradition with the recently reintroduced writings of Aristotle. And he made the point that he didn't think Aristotle was necessarily wrong to think that the world is eternal. The church was fine to believe that it had a beginning, but they ought not to attack Aristotle from Aquinas' perspective and in thinking that he's obviously wrong. When we move to the 20th century, we have Pope Pius XII in the middle of the 20th century, claiming that the Big Bang is clear evidence of God. Bob himself in the late 20th century, early 21st century, is well known for arguing that scientific cosmology doesn't necessarily point us to a beginning in time, but it does point us to the idea of contingency, that the world is not of itself, but is contingent upon something else for its being. And I also wanted to mention William Lane Craig, a philosophical theologian who works as an apologeticist, who has really sort of latched on to the Big Bang and tried to make a lot of hay with it, and thinks that it supports an argument that comes out of medieval Islam called the Kalam argument. It's a very simple argument. It goes like this: everything that begins to exist has a cause. The universe began to exist, we know from the Big Bang. Therefore, the universe has a cause. All right, so this is Craig's argument. Now, whether the universe did begin to exist and whether we know that or not is, of course, I think much more of an open question than Craig sometimes lets on. But for the sake of apologetics, he's pushing that argument quite strongly. Of course, I should mention as well, just to round things out, process thought and process theology, which kind of brings back the notion of an eternal universe, rejects the notion of creation out of nothing. In fact, it's one of the arguments that process theologians give for why their view is better, right? It's more biblical. It's not a beginning moment in time. It's God bringing the world gradually to be. So that's a very short history of Western religious cosmogony. Now to give you a brief introduction to modern scientific cosmogony. I mentioned general relativity, which I'll abbreviate with GR. What does general relativity give us? Well, it's the basis for modern cosmology, and it gives us seemingly a cosmic singularity. Scientifically, a singularity is it's not so much a concrete thing as what happens when the equations stop working. When the radius of the universe goes to zero, when its temperature and density go to infinity, the equations break down, and scientists call that a singularity. And it looks like, at least on the standard model of inflationary Big Bang cosmology, like we have a universe that began in a singularity. Now, Einstein himself famously did not particularly like this. He saw this implication in the theory, and he added this term that I've circled there, the cosmological constant term, as a way of re-eternalizing the universe. Right? He saw that the solutions to his equations gave a universe that was changing dynamically and expanding, and extrapolated, like others did later, that, well, that implies a beginning point. And so Einstein himself said that that's not the way that I think about the universe. So, and he was genius enough to think of a way to modify his equations to fit his own metaphysical perspective. Of course, Hubble in the 1920s, teens and 20s, showed famously that the universe is in fact expanding, like Einstein's the simpler version of Einstein's equation seems to allow, if not suggest, with a velocity that's proportional to the distance that things are apart. So the farther they are apart, the faster things are moving away from each other. Einstein tried to reconcile his own view of an eternal cosmos with this new discovery of Hubble. And he suggested what's called a bouncing cosmology, the idea that the universe inflates, comes back down, gets bigger, smaller, and it just bounces, right? If you've got infinite number of bounces, then, well, maybe you have an eternal universe after all. But another physicist of his day, Richard Tolman, pointed out that the dynamics of the bouncing process means that each bounce is actually a bigger bounce. But if it's bigger forward in time, that means it's smaller backward in time, which means that you eventually get to a singularity again. The bouncing cosmos doesn't save Einstein from this apparent beginning to the universe. So it looks like, from Big Bang cosmology, that our cosmos does in fact have something like a beginning. The Belgian priest Lemaitre talked about it as a kind of primeval atom that exploded. He used and thought himself in kind of theological language. He contributed to the theory, was himself a cosmologist, but interpreted it as a kind of initial primeval explosion that gives birth to the universe. We get the term Big Bang from another cosmologist, Fred Hoyle, who actually the term was a term of derision for him. He thought the idea was silly, and he had his own view of an eternal universe. He called it the Big Bang theory, and that stuck. So that's what we have today, thanks to Hoyle, much to his chagrin, I'm sure. So what does it look like, the standard Big Bang model? This is a diagram from ESA, the European, actually, no, sorry. This is from, I believe it's the Planck or Kobe, one of the satellite experiments that looked at sort of mapping the universe, and one of the key features of it, the microwave background, which I'll get to in a second. But what you have here is from left to right, moving forward in time. You have a beginning point, quantum fluctuations, maybe that's a guess, an initial singularity. I typed that in. They don't have that, didn't have that on the diagram, but that's another possibility. You can sense maybe a little bit of the bias against that by the fact that they chose to leave that off. Then there's a period of rapid expansion, followed by what's known as the cosmic dark ages, where you don't yet have stars forming, but takes about 400, half a billion years, and you get the first stars. And then things keep coalescing and the development of galaxies and planets. And you'll notice that this cone starts to flare out at the end. And that's because within the last 30 years or so, people have discovered that the universe is actually accelerating in its expansion, not just getting bigger, but getting bigger faster. Two of the key satellites that are, well, one of the key satellites that gave us this picture, WMAP, the Wilkinson map satellite, that's already flown, and we have that data. The Webb telescope, so if any of you are following this, that's been a long time in coming. It's the successor to Hubble, and it will be launching in December. It will not necessarily, the Webb, give us much more insight into the cosmic origins. It's more focused on exoplanets, measuring and looking at their atmospheres, sort of the fine details of the universe. So how do we know that the universe is expanding, and what kind of evidence do we have? Well, Hubble's evidence in the 20s was the first important piece of evidence. But a second piece of evidence came in 1965 in the form of this data that comes from a radio telescope. Penzias and Wilson famously were using a radio telescope to look out into the night sky, and there was this sort of background fuzz that they could not get rid of. And they cleaned their telescopes, they shooed the pigeons away, and still they couldn't get rid of it. And it turns out that what they were looking at is what's now called the cosmic microwave background. It's a bit like, rough analogy, the glowing embers after a fiery moment, a fiery beginning explosion. So it's a sort of a smoking gun. It was the discovery of this was what sort of put the nail in the coffin for Hoyle's view, because his view couldn't account for this. And what you see there, that green color represents a very faint and very cold, but nonetheless non-zero background temperature to the universe, just about 3 degrees above absolute zero. But if you're going to get a universe that has structure in it, it can't be perfectly uniform. There have to be small variations in the temperature that are leftover remnants or signatures of early instabilities and density differences that led the universe and the matter in it to start to collapse. Without some sort of non-uniformity, the universe just continues to expand and nothing interesting happens. So it was theorized that if we could look and see this background in enough detail, that we would in fact be able to see variations of temperature. And that's what you see in the middle diagram. The Kobe satellite from 1992 was the first satellite to see clearly these small variations in temperature. They're represented on this diagram by color, and those temperature differences are very, very small. I believe it's about 1/10,000th of a degree. So hardly any variation, but it's enough variation to get the kind of universe that we have today with the structure that it has. 2003, that's WMAP, the follow-on satellite, and clearly you've got a much more high resolution picture there. Things have only gotten better and better in terms of our ability to resolve these temperature differences. The Planck satellite is one of the most recent satellites to investigate the cosmic microwave background, and it's what are called the anisotropies, these small differences in temperature. These are at various different wavelengths. Some of these images are actually, I think, kind of elegant. The lower right one has always struck me as sort of haunting. What you see in the middle of all those pictures, right, is our galaxy getting in the way, right? So you have to subtract that out to get the actual background of the universe. So it really does look like, according to the best scientific cosmology or cosmogony of our day, like the world, the universe that we live in has a beginning in time. But is that really the case? There are a number of problems. First of all, general relativity can't be the whole answer. It's the basis of Big Bang cosmology. But if you wind the clock back and the universe gets smaller, at some point it gets small enough that quantum mechanics ought to be relevant. And so you're going to need a quantum theory of gravity, which is one of the, if not the holy grails of contemporary physics. And we don't have that yet. We don't have the whole answer. We don't have a theory that we think can do justice to the dynamics of those first moments. So leads people to question whether or not there really is a beginning in time, whether that's what the theory is telling us. There are also, I think, reasons to find it unsatisfying, intellectually unsatisfying, to accept the idea of an absolute beginning, right? That we can't investigate behind, that we can't go beyond. That just seems, I think, to many scientists, many cosmologists, like a kind of untoward barrier, just an undue barrier on their own investigation, a kind of constraint that they're not willing to accept, at least not without giving it a good try and trying to imagine what might have come before. Of course, there is the logical point that mustn't every beginning have a before? Is it possible to conceive of a beginning without a before? Does that even make sense? So if every beginning needs a before, then this can't be an absolute beginning. There's got to be some story to be told about what happens to the universe and in the universe with the universe before what we now call the Big Bang. Finally, and not for all, but for some, the idea of a t=0, of an initial temporal point out of which the universe emerges, smacks of creation. Not, as I said, not all cosmologists are concerned about this or find this problematic, but some do, and some are motivated by this sense that we're going to sort of open the floodgates back up to religion and to a pre-scientific age if we can't figure out how to eliminate this t=0 so that we can stop talking about, and in seemingly religious language, about this notion of creation. So some are motivated by a kind of theological or anti-theological, if you will, concern to avoid the implication of there being a kind of clearly implied creation happening at the beginning of the universe. So I think it's a very interesting question for scientists to wrestle with. Is t=0 from the Big Bang a theoretical insight? Is it something that the theory is telling us that we can say we know about the universe? Or is it a defect in our current theory, surely to be replaced in some future time by some better, more complete theory? My sense of the literature and cosmologists today is that most of them regard it as a defect, a theoretical defect. It's something that will go away. If only because the bet is on quantum gravity, right? That's going to make this problem, this non-issue, disappear. Once we have a quantum theory of gravity, then we'll see how the universe doesn't actually have an absolute beginning, but emerges from some pre-quasi-Big Bang past. So that's I think, an interesting and live question. You know, how do physicists decide whether what they're looking at in their theories is an insight or a defect? I think that's an interesting philosophical question for physicists and the rest of us to ponder. So, if the consensus amongst physicists and cosmologists today is that we really ought to and probably will be able to avoid a t=0, what's the likelihood of that? And are there any problems, any obstacles in the way of that, aside from not having a quantum theory of gravity? Well, the singularity, this idea of a t=0, is part of the standard Big Bang model. And in fact, in the 1970s, Hawking and Penrose showed that given reasonable physical assumptions, gravity is always attractive, there's enough matter in the universe, a cosmic singularity is unavoidable. Now, this is just speaking in terms of general relativity, not adding quantum mechanics. But if we just take general relativity, its equations, the dynamics that we understand to have been operative, you can't get rid of an initial singularity. So that seemed like a kind of a no-go argument for an eternal universe. In 1994, Board and Vilenkin improved on the work of Hawking and Penrose and showed that even in an inflationary universe, in between 1970 and 1994, the idea of inflation came along. That's the initial rapid expansion. And they showed that even a world that has what's so-called eternal inflation, that just keeps inflating, pockets of inflation constantly going on, it never ends. Somewhere in the universe is inflating. Even in that scenario, there has to be a beginning. You can't get around that. So in other words, it's not eternally inflating or eternally deflating into the past. More recently, there's been a theorem been developed by Board and Vilenkin, but with Alan Guth, one of the people who came up with the idea of inflation, a slightly different argument. It's an argument that's not based on general relativity. It's a geometric argument about space-time. And the only assumption that they say they need to make this argument go is that on average, the universe has been expanding from the beginning until now. And if that's the case, then according to their theorem, you get what's called a past incomplete universe, which is to say you can't go all the way back along world lines. The world lines come to an end. And if they come to an end in the past, that implies a beginning. So here's a quote from Vilenkin. This is 2015, a bit more recent. The answer to the question, did the universe have a beginning, is it probably did. We have no viable models of an eternal universe. Those are fighting words, by the way, but that's his view. The BGV theorem gives us reason to believe that such models simply cannot be constructed. But as I mentioned, there are a number of things that give people pause when it comes to these claims that we can't avoid a beginning. One is the fact that the expansion now appears to be accelerating. If that's true, and if dark energy is responsible for this acceleration, then perhaps all bets are off. We don't know how to incorporate that into our current cosmological models. And maybe when we do, we'll see that the beginning goes away. On the other hand, we've got quantum mechanics still not incorporated. Maybe there's some sort of quantum transition instead of an actual singularity that signals an important moment, of course, in the life of the universe, but not an absolute beginning. And then there are alternative models. Vilenkin says we don't have any viable models of an eternal universe, but that hasn't stopped people from trying. Let me give you just a sense of some of these models. If the standard view with a space-time singularity at t equals 0, a beginning, is the Big Bang, then there are a number of other models that people have developed as attempts to get around this notion of a beginning. Hoyle, whom I already mentioned, argued for the endless expansion and filling of space. Hoyle's view, most people today, I think, would say is a kind of non-starter. There still are some people who try to work with it and resurrect it, so to speak, but it does not enjoy a wide following today. There's Hawking's proposal, what's called the no boundary, that the universe has a past boundary, but not a temporal beginning. He makes that case in his popular book, Brief History of Time. Another theorist, Veneziano, argues that there's one big bounce, that the universe comes from infinitely large down to a near point, but bounces, and then we get our universe. So it's still a Big Bang universe, but it doesn't have an absolute beginning. It has an eternal past and a kind of fulcrum point in the middle, and then the universe that we know as our own. Endless bouncing. Steinhardt and Turok have argued for a kind of cyclical model akin to what Einstein argued in the 1930s. They think that they can get around the problems that plagued Einstein's own view. They've been arguing for a kind of cyclical model, again, giving us an eternally bouncing, if you will, model. Another view that I've come across in my own research, I don't see this one mentioned very much, but the idea of a long wait, that there's a kind of macro timelessness to the universe. And then the universe at some point in this sort of quasi-timeless reality, time begins and the universe that we know emerges out of it. I can't say much more about that one, but I have seen it referenced in the literature. And again, it's the interesting thing to note about it is that it too tries to avoid a t equals 0. The only view that I know of that's sort of on offer currently that does not try to avoid a t equals 0 is a view, not surprisingly, advocated by Vilenkin, one of the three who developed the theorem that I mentioned earlier. And he argues for a quantum view. Now, short of quantum gravity, this is all quite speculative, but he suggests that with a universe whose net energy is 0, that's the meaning of that little equation there, that you can get a kind of tunneling event such that the universe that we know tunnels out of the nothing, or the no energy that is prior to our universe, or at the beginning of it. He thinks that this is a way that may ultimately allow us to talk about and to model the actual beginning of the universe. Notice, though, that each of these alternatives posits a universe without a beginning, except, of course, for Vilenkin. There's a lot of energy that's been spent on trying to come up with alternatives to the Big Bang because of the dissatisfaction that people feel with it as a model of our universe and its origin. So we're kind of at a present stalemate, unfortunately. We have a bunch of theories. The Big Bang is the standard model, a variety of alternatives, and more or less, they all pretty much fit the data. This is data from, I believe, from Planck, the Planck satellite, and this is a characterization of the cosmic microwave background. And you don't need to know how to read these graphs. The only thing I want to point out is to look at how closely the dots fall near to the line, right? The line is the theoretical prediction. The dots are the measured values. This is extremely well confirmed. And more or less, all of these different approaches claim to be able to reproduce this data. So we seem like we're at a kind of stalemate, like what's going to break the tie? Right? There is recent work by Vilenkin that I want to mention, in which Vilenkin and Metheny argue that just like Einstein, these other models that purport to avoid a beginning, in fact, can't avoid a beginning. So that's currently under debate. But in any case, we seem to have hit a kind of stalemate. And for those of you who were alive in the 1980s and enjoying your first Macintosh computer, you might remember this image. This is from Battle Chess, one of the first games on the Mac. And this is what you saw if you reached a stalemate in Battle Chess. Stalemate, how boring, Apple told you. And it is frustrating to have a stalemate. And what's exciting about gravitational waves is that they have the potential to break this stalemate. And this is where Strigil marks come in. If you might recognize the upper image there as I'm not sure whether it's Roman or Greek, probably Roman sarcophagus. Romans liked, and Greeks liked to decorate their sarcophagi with strigil marks. Strigil marks come from the tool, the strigil, that athletes used and bathers later to scrape off the oil and the sweat and the dirt after either being in a bath or being in a sporting event. They would use these strigils, and they were made out of bronze, and they left marks on your body. And so people sort of picked up on these strigil marks and began to use them as a decorative motif. So in the classical world, strigil marks, these kind of wavy lines, came to represent death, as insofar as they adorned the sarcophagus, the flesh eater in which the body was placed. But today, I think that we've got an interesting kind of reversal. We've got a kind of strigil mark appearing in the universe that's not about the universe's death, but potentially about the universe's birth. And that's in the form of gravitational waves. So let me tell you a little bit about gravitational waves. They are ripples in the fabric of space-time. Space-time, famously, in general relativity, is curved. And mass curves space-time. Mass tells space-time how to curve. Space-time tells mass how to move. They do this sort of elegant dance, space-time and mass. And if mass moves in the right way, and it's the right kind of mass, you can actually get ripples in this curvature. And that's what physicists talk about. That's what they mean when they're talking about gravitational waves. It is, in fact, the squeezing and stretching of space. Here's a simple little image from the web. Imagine that this is a ring of grapes suspended in empty space, and a gravitational wave passes through them. So either into the plane of your screen or out of the plane of your screen. What does it do to these grapes? Well, it does something like this. It squeezes them and stretches them back and forth at the frequency of the gravitational wave. Right? It's a very odd kind of behavior. Here's a more sort of dramatic rendering of it. This is a kind of in 3 dimensions. Hopefully it will come up. Yeah. So here we've got, notice the last circle, the last ring is being squeezed and stretched, right? So the first circle is being squeezed and stretched. And what's happening here is that squeezing and stretching is being propagated from right to left through space. So that's something like what a gravitational wave looks like if you could see them traveling through space. It's what gravitational waves do to matter. It stretches matter one way, squishes it the other, and then that reverses and back and forth. Let me get past that. Sorry. Oh, there we go. All right. So squeezing and stretching of space. This is extremely difficult to detect. This stretching and squeezing is incredibly small. It's a very, very small effect. If the distance between 2 grapes is L, the amount that they change, delta L, is on the order of 10 to the negative 21, right? So 1 part in 10 to the 21 is how much they move out of alignment when they're being stretched. So that's the kind of minuscule motion that scientists have tried to figure out how to detect. The first evidence of gravitational waves came back in the 1970s. It was indirect. If you've got a binary star system, binary pulsar system in this case, and they orbit each other, that's the kind of arrangement of mass that will give off significant gravitational waves, and they carry away energy. So the idea was, let's find a pair of pulsars and watch and see if they spiral into each other and lose energy in the amount that general relativity would predict that they are losing it if they're losing it to gravitational radiation. And Taylor and Hulse, I believe, won a Nobel Prize for this work because they did in fact show that yes, the binary star system did lose energy at exactly the rate that Einstein's theory said they should if they're radiating away that energy in the form of gravitational waves. More recently, then you've probably heard about this in the news, LIGO, the Laser Interferometer Gravitational Wave Observatory, now known as LIGO. I'm not sure how you pronounce it, LIGO, Advanced LIGO. It ran from 2002 to 2010 in its original form, and they saw nothing. And people got pretty nervous because hundreds of physicists had dedicated essentially their careers to building these massive 4-kilometer-long interferometers. And then they shut down in 2010, underwent an upgrade. And in 2014, it was upgraded around 2014. They turned it on, and in 2015 saw their first gravitational wave signature, saw the kind of stretching and squeezing of the arms of the interferometer. So notice the grapes up above, right? Well, imagine that circle of grapes sitting on top of this interferometer. Right? One arm of the interferometer gets stretched, the other one gets squeezed. That shifts the relative phase of the laser going through them, and so they interfere constructively or destructively. And so you get fringe patterns that emerge and disappear at the frequency of the wave that's passing through them. So they found dozens since then. This is a success story. There are thoughts. The European Space Agency would like to put a much larger interferometer into space, not going around the Earth, but actually in a heliocentric orbit like the Earth, with arms that are very far apart, on the order of, I think, hundreds of thousands of miles, if not millions of miles, very far apart. And it's sensitive to a different set of frequencies. And of course, it's in space, so you don't have to worry about trucks driving over your interferometer and messing up the noise. And so we'll see if that happens, but it's not scheduled now until 2034. So that's gravitational waves. It is a kind of new, it's a new kind of physics. It's further confirmation of general relativity. It's provided the most concrete evidence that we have to date of black holes, because some of these gravitational waves signatures that they've seen with LIGO could only have come from a pair of black holes orbiting each other and then coalescing in on each other and losing enormous amounts of energy to gravitational waves in the process. It's a new window onto the universe. It's like getting a new set of glasses that allow you to see in a different part of the spectrum, right? Not the colors you're used to, but colors you've never seen or heard of before. So this is an exciting time to be an astronomer and cosmologist working in the world of gravitational wave physics. So here's the payoff. Gravitational waves are thought to have originated in the very first moments of our cosmos during the inflationary period. And whereas radio telescopes and visible light telescopes cannot see back past the cosmic microwave background, which is essentially what happens when the universe turns about 400,000 years old, right? So we can't actually see earlier than 400,000 years. A universe that's 400,000 years old, we can't see earlier or behind that, right? Telescopes are time machines because of a sort, because light travels at a finite speed, right? So the further away something is, the earlier it happened when the light gets to you, right? So we can actually see back in time, but there's like a curtain in the universe. It's the cosmic microwave background, and we can't see behind that with the telescopes that we've developed prior to gravitational waves. But if we could develop gravitational wave telescopes, and as you might guess, people are thinking about that actively, then we might be able to see the gravitational waves that originated in the early universe. And what happens to be the case, what interestingly turns out to be the case, is that these different models that I mentioned earlier, the Big Bang, the ekpyrotic, the cyclical, the pre-Big Bang, all of these models make different predictions for what kind of gravitational waves would have been generated in the earliest moments of the universe. So maybe if we could detect these gravitational waves coming from the early universe, we could put some empirical pressure on this debate about whether the universe has a beginning and actually maybe get past the stalemate that we're currently in. Now, as it turns out, the ground-based interferometers that we have now, the current generation, they're not sensitive enough to detect primordial gravitational waves. They can detect gravitational waves from in-spiraling black holes and other objects in the universe, but not the incredibly faint signature of gravitational waves coming from the earliest moments of the universe. So, is there hope of finding these primordial gravitational waves? They are thought to leave an imprint on the cosmic microwave background in the form of a kind of polarization pattern. And everybody got really excited in 2014 because an experiment that was running down, I believe, in Antarctica, thought they saw this kind of polarization pattern. It turns out that with data from the Planck satellite, which was also flying at the same time, it turns out that what they were actually seeing was polarization patterns caused by dust in our galaxy. So it was a false positive, and they had to retract their claim. Now, the efforts at trying to figure out how to subtract out that dust pattern are ongoing, and it may well be that eventually we are able to see the imprint of the cosmic gravitational waves from the earliest moments of the universe, to see their imprint on the cosmic microwave background. And that could provide us with evidence and data that would help us discriminate between these different alternative cosmological theories that are on offer today. So it's called various names. I call it the cosmic gravitational wave background, or primordial gravitational wave background. It separates out from other matter at the first moments after the Big Bang. So as I mentioned, we can see, if we had telescopes that could see this, we could see back before the CMB. And as I said, the different models make different predictions. Here's a quick just tour through some of these predictions. Again, all I want you to pay attention to is the fact that these the different lines look quite different from one another, right? So this is what a black body universe, earliest universe looks like, just a very simple model of the universe, peaks at around gigahertz range. This is the inflationary Big Bang prediction, a kind of flat spectrum from very long wave to very short wave gravitational waves. Here's what the cyclical model predicts. So quite different than the other two. And here's what the pre-Big Bang model predicts. So all of these are quite different from each other. And if we had the instrumentation to see it, we might be able to confirm or disconfirm the predictions of some of these theories. Here's just a quick glance at the sensitivity of the various instruments. Advanced LIGO maybe can reach down eventually into the pre-Big Bang territory, but it can't make it all the way down to the level of inflationary Big Bang. LISA, the not terrestrial, but space interferometer, makes it down as well into pre-Bang territory, but again, doesn't quite have the sensitivity to get down to the cyclical and inflationary models. The Big Bang Observatory, that the BBO, that is something that's sort of a, it's a sparkle in someone's eye at this point. It would be nice to do, and it will be many decades before that happens, if it ever does. The Planck satellite, by the way, did rule out some inflationary models, but not the basic idea of inflation. So inflation's still on the table. I was fortunate enough to do some work with a physicist out in California, Raymond Chow, who's now at University of California at Merced. And we did some work on gravitational waves. This research was funded by CTNS, the STARS project, the Science and Transcendence Advanced Research Series. And I learned a lot about gravitational waves from Ray and from my experience with his group. To my knowledge, we haven't spoken in a while. I've not heard any big news out of Merced. I think they're still trying to develop the ideas that Ray has, but no breakthroughs there as of yet. But I'm deeply indebted to him and to CTNS for the grant that enabled me to work with him. All right, so a few thoughts about theology and science and beginnings. To begin or not to begin, that is the question, cosmically speaking. Does the universe have a beginning or not? The cosmological debates are ongoing, and as I've suggested, there are two camps. There are a few voices out there who want to say, look, we need to face up to this. We really do have what looks like a beginning, and we can't get around it. Vilenkin is that voice in the discussion. Most others, though, like Sean Carroll, think that it's a defect and think that it just doesn't make sense to talk about an absolute beginning that has no before. So Carroll and most cosmologists these days put their money on the idea that t equals 0 is going to go away eventually when we have a better theory. Now, there's no clear gravitational wave evidence so far against the inflationary model, and there's no clear gravitational wave evidence for the eternal models. But I think that it's very likely that future generations of these detectors will be able to see with enough sensitivity to actually see the cosmic primordial background, gravitational wave background, and will, I think, contribute to this debate and move it forward. So what are we looking for here as theologians from a scientific theory about the origin of the universe? What would it mean to have a theory that's consonant with a theology of creation? Now, the Christian doctrine of creation does not require a beginning. As Aquinas pointed out, as Bob has argued in a number of his works, contingency is really what the doctrine of creation is about, fundamentally. Now, one way that contingency could be expressed is through the notion of a beginning moment. And I want you to think with me for a moment, if there were a cosmic beginning, let's just say, except for the sake of argument, that there was a cosmic beginning by divine fiat, right? That something like the story of creation out of nothing is what actually happened. What would we expect or hope a scientific theory about that beginning to look like? What would we want from a scientific theory? Would we want a theory that breaks down at the moment of the beginning? Would we want a theory that doesn't talk about the beginning itself, but can only talk meaningfully about what happens after the unexplainable beginning, when the equations break down, right? Something like what we have in the current Big Bang model. Would we want an actual mechanism, a theory that gives us an actual, say, deterministic physical mechanism rooted in laws that somehow, for the sake of argument, point to their own necessity, right? So it really is a complete, scientifically complete theory of the origin of our universe. Is that what we would want? Or would we want a quantum random mechanism, some sort of physical mechanism coming out of quantum gravity, with the universe tunneling its way out of nothing, right? Is that the kind of scientific theory that we would regard as being consonant with a theology of creation? Or is it something else? These are the options that are on offer today, that people have developed, in the last century, and there may be others. I'm not enough of a cosmologist to think of any on my own, but these seem to me to be the options that are out there right now. So let's take a look at each of these options. Unexplainable beginning with equations breaking down. So how is a physicist going to respond to that kind of theory? Well, I've talked about that a little bit already. Sean Carroll and others basically see this as problematic, right? The absence of a more complete mathematical framework that can talk about the t=0 moment and not just what happens afterward, they regard as unfinished business, right? That needs more work. And they're not going to rest until they have in their hands a theory that does that work, that gives them a mathematical and physical account of not only the subsequent development, but the actual beginning moment, if such there is. Now, what does that look like to theology? Well, I think this kind of, the notion of a theory that's necessarily incomplete, I think could appeal to a kind of super or anti-rationalist sensibility, right? What you've got here is the divine perspective transcending or defying rational description. We're going to be stuck with a theory, says the theologian. We're going to be stuck with a physical theory that is never complete because creation itself goes beyond what science can describe. Right? So it might be appealing to a certain theological mindset to have a theory, a scientific theory that is just forever incomplete because of a sense that in order to complete that theory, you can't rationally complete it or extend it. You have to go beyond rationality. You have to move into the realm of the transcendent or the divine to understand and to see that the world actually is created. So I think there's potentially some theological consonance with a particular kind of theological perspective there. Now, what about the other two? Some kind of complete mechanism, whether it's deterministic or random. What's the physicist going to say about that? Well, I think the answer there is going to be that the physical mechanism is simply sufficient unto itself. We don't need any more explanation. If we've got a mechanism, then why not just accept that as brute fact? Here's how it started. We know how it started. And perhaps we can even see something like necessity in why the laws are the way that they are and not some other way. And they give rise to our universe. So we've got a kind of complete necessary picture from the physical point of view. Not necessarily friendly to theology. I think the physicist is going to say, I've got what I need in my physical theory. But the theologian, on the other hand, I think will find, a certain kind of theologian will find this appealing. And it's the kind of theologian who has a more rationalist sensibility, right? Who thinks about the divine perspective not transcending or defying the human rational description, but supplementing it. Think here of sort of the medieval Thomistic view of the Aristotelian description of the world, and then on top of that, the theological description, right? They're not in conflict, but one supplements the other, right? I think someone who sees the world, a theologian who sees the world in that way, would be more inclined to think that the kind of physics that we need is actually a physics that really does tell us how the world begins. Right? In fact, I think this is a sort of, I find it anyway, a kind of interesting manifestation of an age-old problem in Christian theology, namely the relationship between nature and grace. It's, I think, a kind of new take on an old problem. Traditionally, of course, the question of the relationship between nature and grace is the question of the doctrine of salvation, right? And how salvation happens and what is changed and what's possible. Right? But here I'm talking about the doctrine of creation. And there's a kind of relationship between nature and grace that's manifested in these two options, right? Either grace transcends and defies nature, and there's a kind of uncrossable gap between our understanding of the world and its origin and the way things actually happen, right? And if this is your sense of how grace and nature relate, well, then you might expect to find a physically incomplete account of the origin of the cosmos. On the other hand, if you think that grace supplements nature, then the uncrossable gap becomes a very crossable and possible step to take. Not that one has to take it, but if one's theologically inclined, then you see in the otherwise scientifically complete account of creation, the beginnings of a larger story that can be folded into a theological narrative. So if you have the theological sensibility of grace supplementing or completing nature, then I think you might expect a physically complete account and might want one. Right? So I think the different theological sensibilities will look at this situation a little bit differently. Here's where I come down. I think that science has an internal bias toward a kind of pan-rationalism, never giving up on rationality. I think scientists and cosmologists will always prefer what appears to be a more complete account of cosmic origins. Now, in theology, I think in some instances you have a bias toward pan-rationalism, and in other places you find a bias towards super-rationalism or anti-rationalism. Both of those exist in the history of Christian theology. But for me, a theological appreciation of science tips the scale toward pan-rationalism. I think that we ought to welcome the possibility as theologians of a gravitational wave physics that advances beyond the sort of the Big Bang incomplete physics scenario, and gives us a physical story of cosmic origins that takes us beyond our current understanding and actually gives us something that might, from a physical point of view, look complete. That said, I will end with a caveat, not to the buyer, but to the learner. Caveat discipulus. In contemporary cosmology, knowledge and ignorance can, I think, be difficult to distinguish. In fact, sometimes it feels to me like they coalesce in ways that would have made Nicholas of Cusa, the author of On Learned Ignorance in the 15th century, who was also, by the way, a theologian and an astronomer, smile, to say the least. So thank you for your attention, for your time. Thank you especially to Bob and to CTNS for the invitation to deliver this public lecture. So, thank you.
Thank you, Kirk. That was fantastic. Just a great tour de force. And I really like the way you present it. It's so inviting and relaxed, and yet so detailed and complicated. We have time for a brief response from Hongzhou Li before we take questions from the audience. Hongzhou?
You hear me?
Yes.
Thank you, Bob. First, I'd like to mention that I was privileged to be a respondent to the previous Russell Fellow, Dr. Adam Pryor, last year. It's really an honor for me to be invited as a respondent again to another Russell Fellow, and now my friend Kirk this year. I'm really grateful for these wonderful opportunities given to me. At the last year conference, I responded quite critically, I remember that. However, I'm aware that unlike last year when I gave a response at the research conference, at this time I'm at the public forum, and my job is not to initiate a strong debate. So rather than imposing a critical argument, as a one who has a little knowledge of scientific cosmology, I would like to supplement what Kirk already brought in very well from various theories for scientific cosmology. From the outset, Kirk emphasized the interaction between the religious cosmogony and the scientific cosmology. I am aware that he intendedly used the word cosmogony even when he talked about scientific cosmology. I understand his context. However, I would prefer to avoid naming any scientific cosmology as scientific cosmogony for two reasons. First, we don't yet have a single scientific theory which unveils the origin of the universe without a controversy. It is clear that all the cosmologies we have describe our universe more or less scientifically. But it might be controversial to say that all the different cosmogonies separated from them alone could be also called scientific as well. For example, Newtonian mechanics is a scientific theory for sure, but what it predicts are not always scientific. We don't say that the speed of light could change scientifically, even though Newtonian physics assumes it. I'm not saying that we should not use the term scientific cosmogony at all, but we might need a pause before we take it granted that all different cosmogonies from scientific cosmologies should be called scientific. Second, and this is indirectly related to what I said just before, the primary concern of a scientific cosmology is not cosmogony. Although it is true that each scientific cosmology could be extended to bring the issue of cosmogony, as Kirk already demonstrated. The reason that I'm now trying to distinguish the scientific cosmology from the religious or theological cosmogony is to emphasize the qualitative distinction between scientific cosmology and theological cosmogony. The primary concerns for cosmologists are often radically different from the concerns for theologians. Nevertheless, as Kirk illustrated throughout his wonderful presentation, they have overlaps, and these overlaps are the place where we could make the interaction between theological cosmogony and scientific cosmology work in a legitimate way. And indeed, each scientific cosmology has its own cosmogony as its byproduct, as long as that cosmology is a theory that describes the history of our universe. So I'm not criticizing Kirk, but rather supporting his argument by adding a warning that we should not be tempted to think that we could just bring any scientific cosmology to theological cosmogony without any effort to bridge them. We can talk about cosmogony with the aid of scientific cosmology for sure. It is valid and more than valuable, but it is not straightforward. And I believe this is the very reason that we have Kirk here and Bob and Ted in the fascinating field of theology and science. Let me conclude by adding another warning that we should not take a single scientific theory to be an absolute counterpart, absolute only counterpart to theology. I believe this is why Kirk did not introduce only one scientific theory, but various other theories at the same time throughout his presentation. I myself published a paper in a scientific journal about a scientific specific cosmological model which predicts cosmological gravitational waves all around our universe with some specific frequencies. I believe the model that I proposed with my colleagues, including my former supervisor in physics, is valid. However, there are, with some exaggeration, thousands of different models that predict different signals, gravitational wave signals. The only reason that they are all surviving is because we don't have enough observations yet. However, in the near future, most of them will be ruled out as our technology develops. When I published my paper with my former supervisor and my colleagues, my supervisor said to me with a joke that our model will be ruled out within 30 years. If it survives even in 30 years, then let's have a big party then. That's what I heard from my former supervisor. I would be really happy if I could have a party with my former supervisor and my colleagues in 20 years. However, I respect various other models which predict totally different signals of gravitational waves and other phenomena. Today, Kirk introduced various cosmological models that would result in different gravitational wave signals, even though he did not introduce mine. Some of them may survive, others will be ruled out. However, I believe we theologians have a lot to say with all these models as long as we keep this in mind and overcome the temptation to say something too easily. That's why Kirk, Bob, and Ted, and I myself exist in this fascinating field. Thank you.
Thank you, Young-Jo. Well presented. Kirk, do you want to make a brief response before we go to the Q&A?
Sure, very briefly, just thank you, Young-Jo, and my apologies for not including your model. I'll rectify that in a future version of this presentation.
I was joking.
I guess my one question for you, Young-Jo, is, do you think that the notion of scientific cosmogony is and will always be a non-starter? Or is that something that we don't have now, but could have in the future?
I think we could have some scientific cosmogony in the future, but I think we need to think about very carefully the criteria to call it scientific cosmogony.
Yeah, sure. Okay.
Great. Okay, we have a few minutes for general Q&A, and Braden, you're going to handle who speaks when. Is that right?
Sure thing. I think in the interest of time, you may want to just go ahead and submit a question, like we already have one up. Kirk, you're able to see the first question there. There should be a question and answer at the bottom of your screen. And if you're not sure about that or you need some help, you can feel free to message me directly, or you can use the raise your hand function, and I'll get a list of people who have raised their hand that want to talk as well.
Yeah. Kirk, unmute yourself.
Right. So how do you feel that religion and access to advances in technology have transformed the thinking of cosmological frameworks? I guess my brief response to that would be that I think they've motivated a good bit of theological work in the 20th and beginning of the 21st century. Have they transformed the way people think about cosmological frameworks? I would say not, but I think that they do inform, as a kind of background, people's interest in this field and motivate people in all kinds of ways to develop different and alternative cosmologies based on their own theological interests. You saw it in Fred Hoyle, you see it in Vilenkin, in Carroll, you saw it in Hawking, right? Lots of examples of people who are motivated by a kind of, if not theological, but a particular metaphysical picture of the world, and want to develop a scientific cosmology that is consonant with that metaphysical view. Should I take the second question? Hi, Tim.
Yeah, and then I have another one lined up after that for you.
Okay. In the various cosmological models, without any T equals 0, to what extent could events that happened prior to the Big Bang affect events that happened afterward? Without such cause and effect, could we meaningfully talk about the relationship between events on either side of the Big Bang? Yeah, I think that that's a great question. In other words, do we really have two distinct universes, two non-causally connected universes that have this common middle point, if you will, but that we can't talk about causal relations between them? I think that has everything to do with the actual dynamics of the bounce. And that's precisely what someone like Vilenkin or Veneziano, with his pre-Big Bang model, admits he does not have. He does not have the dynamics of the bounce. He has a general sense of how this works from an eternal past to a kind of bounce to an eternal future. But in order to get the causal connections between past and future, if there are any, then you're going to need to talk about the dynamics of the bounce itself, and that's going to require, presumably, a quantum theory of gravity. So it's a great question. I think it depends upon the dynamics, and I'll have to think more about whether there are dynamics that might rule out any kind of causal connection. I'm not inclined to think so, but thanks, Tim.
Okay, the next question is from Martin Bobrowski. I'm going to allow them a chance to talk here.
You know, as we learn more from cosmology and have the understanding that at time zero, the beginning of the universe was a very rapid event and the creation is still going on. If we look at examples in the Hebrew Bible, it gives a concept of creation starting and being completed in what is now called 6 days. So I'm wondering whether there has been interplay between theologians and physicists about the concept of time and what that actually represents, and is there a need to confront what seem to be apparent discrepancies?
So if I understand the question, thinking about the biblical view of time being somewhat different from a kind of scientific view of time, in which we have a continuously unfolding dynamical set of processes. But in the biblical view, what you see is a kind of time that begins, a time of creation that begins, but then comes to an end. God rests on the seventh day, I think is what you're referring to. And so there's a kind of end of time. I think that, I guess I would read those texts more in terms of a kind of cycle of and a pattern for human life of a kind of engagement of time and stepping back from time. Who is it? Heschel, I think, who talks about the Sabbath as a kind of moment of time touching eternity. So it's not that time ends with the Sabbath, at least not short of the eschatological Sabbath, but for our Sabbaths, time continues, but we have this cycle that's divinely patterned in the text that allows us to have moments of connecting to the end of time, the beginning of time, but in a kind of a ritualized, repeated manner. So I don't think there's a kind of, I don't see a conflict between the kind of notion of temporality in the Bible and a more scientific notion, though of course that's completely sets aside the whole question of special relativity and four-dimensional space-time, and that's a big can of worms, and I would defer to Bob on that issue. But in terms of what I talked about tonight, I think they're relatively compatible with each other.
We have time for a few more questions. Braden, can you find one? Braden, you're on.
I don't have any written down or any hands up. So if somebody has something to ask, feel free to raise your hand or to put a question in the question and answer spot there at the bottom. Okay, we've got one in the chat there, Kirk, from Jung Hung.
Yeah. Interested in my comment about the theologian's sensibility of nature and grace will affect how we think about the future of scientific theory of cosmic origins. Could you tell us what your preference between the two models, transcendence, defiance, and supplementation? If you could explain your position in relation to the concept of an iota, that would be of great help. I did try to hint at my own view. I think my own theological perspective and appreciation of science makes me want a world in which the two are seen as possibly as compatible with one another, as a theological view that complements or completes rather than transcends or defies a scientific perspective. I think that the problem that I have with views that pit nature against grace, in the end, it's a deep theological question. But for me as a theologian, it comes down to a sense of God's consistency, faithfulness, and it just not really making sense to me in the end that God would create a world that God then has to somehow set aside or defy to make the world what God wants it to be, either at the beginning or at the end. It seems to me that God would create a world, that the God of the Hebrew Bible and the God of the Christian New Testament exhibits the kind of faithfulness that leads to a picture in which God's creation and salvation and relation to the inner workings of creation are harmonious rather than in defiance of or antagonistic toward. So, but that's a pretty, that's a pretty deep kind of basic fundamental theological proclivity that I think, we theologians carry around and don't always spend a lot of time articulating, but it motivates how we think. And for me, that's sort of where I would come down.
Kirk, let me get a quick response to you from my response to Carol. When he says you can't have a beginning without something before it. I think that's from a Platonist view of lost nature, that they exist ontologically and govern nature. And because from that point of view, it only makes sense you have infinite flow of time. If you think of them as a descriptive of nature, then you can say, well, they're simply describing the fact that here is an event t equals 0 for which there isn't a beginning before, but there's an after. So if you were to respond to Carol, would you use something like that, or pick out his philosophical assumption that he hasn't said, or how is it to him?
I guess I would not be inclined to go in that direction, because it seems to me that the problem, though one could talk about it in terms of a Platonic view of law, it's really a deeper philosophical question about whether there can be causal orderings of events in which there is an event that is uncaused,
Okay.
that without prior, right? And that is not. I mean, the theological tradition sort of makes an exception for God, and understandably so, right? God's not the world, so God can be have aseity, be self-caused, not have a before. But if we're talking about creation, then I think it's not just a matter of laws and how one reads them prescriptively or descriptively. I think it really is a kind of fundamental philosophical issue about whether it's conceivable that reality is such that there are moments that do not have priors.
Then could you respond to Carol by saying it's a vestigium Dei? God doesn't have a prior, but God exists. Think about it.
Yeah, that's interesting. That the part of the imago Dei in creation
exactly
is that we have a beginning without a before.
Exactly.
Yeah, that'd be interesting to explore. I like that.
Okay. Well, I'm going to just close up here with a quick note on your calendars, and then once more, a chance to thank Kirk. Our next CTNS public forum is being given by Dr. Hava Samuelson, wonderful friend of CTNS. She's the Regents Professor of History and the Director of the Center for Jewish Studies at the Irving and Miriam Lowe Professor of Modern Judaism, Arizona State University, Tampa, Arizona. Her talk is Transhumanism as Contemporary Idolatry, a Jewish Critique. That's Wednesday evening, 5 o'clock our time, November 3rd. So I encourage you to attend. She's a fantastic lecturer. She was a Russell Family Fellow a few years ago, and it'd be delightful to see her. I really want to close by thanking Kirk for your powerful lecture. Its breath is just takes your breath away. And the nuances you brought to the scientific discussion and then to the implications for theology and how you move between them is really stunning. I look forward to seeing it in print one of these days. And mostly I look forward to the event on Saturday. But before I say that, Hangzhou, thank you for your response. It was subtle and gracious and nuanced. And I know there's much more you want to say and you can say, and we will hear it. It will happen. There'll be an after for this before. Okay. I hope you all join us again on Saturday, this coming Saturday, 1 o'clock Pacific time. Well, Kirk will present his Research Fellows lecture, Engaging Hypotheticals, and there'll be 3 respondents. Until then, I wish you a safe evening and a good night. Thank you.